Hey guys, in this problem we have two particles that are traveling along the space curves defined by the two position functions r1 of t and r2 of s, and we're trying to find out whether their paths intersect and whether these particles collide. So let's start with the first question. Do their paths intersect? So if their paths intersect, well, they do if there exist some numbers, t and s, they don't have to be the same value, such that r1 of t equals r2 of s. So what I'm really trying to say is that we need to obey this system or functions. So t equals, so I'm going to label this my a. I'm going to label this A, B, C instead of X, Y, Z. So that's easier. So this part is A, this part is B, and this part is C. So it's kind of similar to our X, Y, Z's. So A, B, and C. So I'm going to set the A's equal to each other. So T equals 1 plus 2S. T squared, my B's are going to be set equal to each other, so t squared equals 1 plus 6s, and finally t cubed, or my c's being set together, are 1 plus 14s. So this is my set of functions, and that creates my system. Now let's move on to isolating or solving for one variable. I'm going to solve for s. So that I can plug in to any one of these soon. So using the first equation, I'm going to use the first one because it's the most easiest one to deal with right now. So t, if I solve for s, I'm going to get s equals t minus 1 over 2. Now with this from my first my first equation, I'm going to plug this into my second one so that I can solve for t. So t squared equals 1 plus 6 times this. So t minus 1 over 2. So when we solve for t, you can plug this into your calculator. You should get t equals 1 and 2. So t equals 1 and t equals 2. But we need to check whether these two values that we just got are solutions. So to do so, we're going to be solving for s. So solve for s. And then we're going to go ahead and plug it into our third equation to check whether the system or the equation or the values do indeed intersect. So let's test time equals 1 for now. So we have t equals 1. So if t was 1, so going back to our first equation, so if t was 1, s would be 0. If t equals 1, then s equals 0. So all I did was plug in 1 over here. So 1 minus 1 over 2 is 0. Okay, moving on, let's plug that into our third equation. So t cubed equals 1 plus 14s. 1 plus 14s. If I plug in 0 for s, so 1 plus 14 times 0, I get 1. And then for this part, for t, if I plug in 1 for t, so 1 cubed, that also equals 1. Because this is a true statement, 1 equals 1, which equals 1, I know that time t equals 1 is a point of intersection. Now, let's check, or it's a time of intersection, not a point, sorry. Now let's check time equals 2. So if I just make some space for time equals 2, again I'm going to solve for s. Solve for s. So if I plug in 2 for t, so instead of 1 I plug in 2. 2 minus 1 is 1, divided by 2 is a half, so s equals 1/2. Now I'm going to write, so if t equals 2, s equals 1/2. 1/2, perfect. Okay, now I'm going to bring back my third equation over here. So that is t cubed equals 1 plus 14s. And if I plug in 1/2 for s, so 1 plus 14 times a half, I'm going to get 8. And if I plug in 2 for t, so t cubed, that also equals 8. So I know this is all a true statement. These are all true statements. So I know that the two particles do intersect at time t equals s and t equal t equals 2 and s equals 1/2. So when I take my position functions from here, so r1 of t equals t comma t squared comma t cubed, and I plug 1 in because 1 was a valid solution from here. So r1 of 1 equals, if I plug in 1 for each value, so 1, 1, 1 for t, I'm going to get 1, comma 1, comma 1. Similarly, if I plug in 2, so if I plug in 2 for t, I'm going to get r2 of 2, or oops. Yep, okay. R1. Let's stay consistent. Okay. R1, because we're not trying to go to this function yet. Sorry. Equals 2, comma, so 2 squared is 4, and then 2 cubed is 8. And we can check our work by plugging in our s values into the r of 2 function. So r of 2 equals, r2 of s equals 1 plus 2s of s comma 1 plus 6s comma 1 plus 14s. Okay, now if I plug in, since for the first one I got 0, so I'm going to plug in r2 of 0 equals 1 plus 2 times 0 is 1. And then 1 plus 6 times 0 is also 1. And lastly, 1 plus 14 times 0 is also 1. Now if I go here to r2 of, in this case I have a half, so 1/2. This is going to be 1 plus 2 times a half, that's going to be 2. And then if I do 1 plus 6 times a half, that is 4. And lastly, 1 plus 14 times a half, that is 8. So after completing our checks, we realize that both sides produce the same vectors. So therefore the particles particles intersect, and then at 1, 1, 1. Don't forget your vector notation. So we want there we go. Okay, perfect. And then 2, 4, 8. All right, and there we go. So that's our answer for part 1. So the particles intersect at 1, 1 and 2, 4, 8. Now we have our second part to the question. Do the particles collide? So right over here. Now a collision means that the two particles occupy the same point at the same time. So intersection, the particles occupy the same point, but not necessarily at the same time. So in this case, what we're trying to see when they collide is that our times, they're not the same. So, or let's go up here. Okay, so if t equals 1, then if I would need s to also equal 1. So they don't collide at this vector. So no collision. I'm going to write no collision. No collision. So similarly for the second one, we notice that time t equals 2 does not equal s equals 1/2. So 2 and 1/2 do not equal each other. So therefore, this vector does not collide either. So no collision. So the particles do collide the particles do intersect at 2 points, but they don't collide for this question. Thanks.